Hello everybody. In this video we are going to be looking at the solutions to the college prep electromagnetic induction problems 1 through 5. We've studied electricity and we've studied magnetism. Now we're going to put those two things together and see how they are related to one another. So let's take a look at the first problem. We have a wire 20 meters long, moves at 4 meters per second perpendicularly through a magnetic field. An EMF of 40 volts is induced in the wire. What is the strength of the magnetic field? Let's take a look at our given values. We are given the length of the wire, which is 20 meters. We are given the velocity of the wire, which is 4 meters per second. And we are given the EMF that is induced in the wire. Remember, EMF stands for electromotive force. And for our purposes, and for as deep as we're going to get into this, we can think of that simply as a voltage. It's the same thing as a voltage. It's just a potential difference from one end of the wire to the other. Typically, when we're dealing with electricity, voltages were created by connecting a wire to opposite ends of a power source, such as a battery. In this case, we are not connecting the wire to any type of power source. We are creating the voltage by moving the wire in a magnetic field. Remember, a changing magnetic field can induce or create an electric current. So that's all we mean by EMF. And whenever we see EMF, we can just read that the same way we've been reading voltage for our purposes here. We just want to distinguish that this voltage is not created by a battery or a power source. It's just created by a changing magnetic field. And if you notice, when we use this symbol here, instead of V, we're using this funny looking E, which is similar to a Euler's constant. Don't need to know what that is, but we just want to be able to distinguish that that is an induced EMF and not one caused by a battery. And lastly, we are looking for the strength of the magnetic field. So if I want to use, if I want to find the magnetic field and I'm given the EMF, the velocity, and the length of the wire, I'm going to use E equals BLV. And I want to solve that for the magnetic field, or B, so I'm going to end up with B is equal to E divided by L times V. I plug in my known variables for that, and I should get a magnetic field of 0.5 Tesla. Problem 2. An airplane traveling at 9.50 times 10 to the second kilometers per hour passes over a region where the Earth's magnetic field is 4.5 times 10 to the minus fifth Tesla and is nearly vertical. What voltage is induced between the plane's wingtips, which are 75 meters apart? Let's take a look and see what we're given for this one. We are given the velocity of the airplane, 9.50 times 10 to the second kilometers per hour. I do need to convert that to meters per second, and when I do, I have a value of 2.64 times 10 to the second meters per second. I know that the magnetic field is 4.5 times 10 to the minus fifth Tesla, and we are told that it is vertical, so if the plane is flying horizontally, and we sure hope it is, because if it's not, something's gone horribly wrong, but if the plane is flying horizontally and the magnetic field is vertical, then they are opposed by 90 degrees to one another, which is what we want. And they want to know what voltage is induced between the plane's wingtips, which are 75 meters apart. So we can say that if the wings or the wingspan of the plane is a conductor, just like a wire, and they're made out of metal, so they are, then I can say that the length is 75 meters. So we're looking for the voltage that is induced. So we are looking for our induced EMF. And I know that my induced EMF is equal to BLV. That's what I'm already looking for, so I don't need to do any rearranging. I can just plug in my known values into that equation, and when I multiply them together, I am going to get an induced EMF of 0.89 volts. Problem 3. At what speed would a 0.20 meter length of wire have to move across a 2.5 Tesla magnetic field to induce an EMF of 10 volts? In this problem, we are given the length of the wire, 0.20 meters. We are given the strength of the magnetic field at 2.5 Tesla, and we are given the induced EMF of 10 volts. And we are looking for the velocity. So again, we're going to use E equals BLV. In this case, we're solving for V. And we have V is going to equal E divided by B times L. So my electromotive force is 10 volts, my magnetic field is 2.5 Tesla, and the length of the wire is 0.20 meters. I do out that math and I will come up with a velocity of 20 meters per second. Problem 4. You wish to generate an EMF of 4.5 volts by moving a wire at 4.0 meters per second through a 0.050 Tesla magnetic field. How long must the wire be, and what should be the angle between the field and the direction of motion to use the shortest wire? Let's take a look at the magnitude or the length of the wire first, and then we will look at the angles second. So in this problem, we are given the induced EMF of 4.5 volts. We are given the speed of the wire at 4.0 meters per second, and the magnitude of the magnetic field at 0.050 Tesla. To find the length, we need to use E equals BLV. In this case, solving for length will yield L equals E divided by B times V. We plug in our known values into the equation, and we are going to have a length of 23 meters. Now let's take a look at the angles. In order for us to be able to use the shortest length of wire, we're going to need to be able to induce the EMF in that wire. We know that the wire and the direction of motion of the wire are both going to have to be perpendicular to the magnetic field. So all three of those things need to be at right angles to one another. In other words, one has to be on the y-axis, one has to be on the x-axis, and the third has to be on the z-axis. Problem 5. You connect both ends of a copper wire with a total resistance of 0.10 ohms to the terminals of a galvanometer. The galvanometer has a resistance of 175 ohms. You then move a 10 centimeter segment of wire upward at 1.0 meters per second through a 2.0 times 10 to the minus second Tesla magnetic field. What current will the galvanometer indicate? Now this problem is a little bit tricky because you're given two different resistances and you have to determine which one you're going to need to use. But before we can find the current going through the galvanometer, we're going to need to know what the voltage is, or more specifically, what the induced EMF is going to be in the wire. So we are given the resistance of the wire at 0.10 ohms. We're given the resistance of the galvanometer at 875 ohms. We're given the length of the wire, which is 10.0 centimeters, which is going to need to be converted into meters. So that's 0.100 meters. We are given the velocity of the wire at 1.0 meters per second and the magnitude of the magnetic field at 2.0 times 10 to the minus second Tesla. And we are looking for the current. So as I said, in order to find the current, because I already know the resistance through the galvanometer, I need to know what the induced EMF in the wire is going to be. And to find that, I use E equals BLV. So plugging my known values from magnetic field, the length of the wire, and the velocity of the wire into that equation, I'm going to get an induced EMF of 2.0 times 10 to the minus third volts. Now I know the induced EMF going through the wire. I know the resistance of the galvanometer. So now I can determine what the current through the galvanometer is going to be. And remember, I told you in the beginning of the video that we can interpret the induced EMF and the voltage as the same thing. So I can use Ohm's law to find the current, substituting my induced EMF for the voltage in Ohm's law. When I solve Ohm's law for current, I have the current is equal to the voltage divided by the resistance. So I know that it's going to be 2.0 times 10 to the minus third volts. That's my induced EMF. And because I am looking at the current going through the galvanometer, I need to use the resistance of the galvanometer in Ohm's law. So I have to use 875 ohms. When I do out that math, I am going to get an answer of 2.3 times 10 to the minus 6 amps, or I can also write that as 2.3 microamps.